Okay, well, welcome again to our work on analytic number theory. We're up to chapter 4, and in this chapter we're going to introduce characters, L series or L functions, and also we're going to have a look at Dirichlet's theorem. So this is a fairly self-contained chapter. So in chapter 2 we use the properties of integers and primes to prove that certain arithmetic progressions contained infinitely many primes. We proved there were infinitely many primes, for example congruent to 1 or minus 1 mod 4, and there are similar proofs. You can prove infinitely many primes congruent to 1 mod 8 or minus 1 mod 8. But all of these proofs rely on subtle observations, and there didn't appear to be any way of generalizing these. And so we now want to seek a more general way of approaching such problems using analytic tools. And in order to do this, we need some method of lifting the integers into the complex numbers, and this is going to be done via the notion of characters. Now, characters come from a much more general part of group theory, and they're simply homomorphisms from a group G to the complex numbers. And there is a general theory of characters for finite groups, but what follows, we're going to be only interested in abelian groups. So finite abelian groups. So when I use the word group, I'm going to mean, without saying it, G is a finite abelian group, and our characters will be defined on that. So a character then is going to be, just think of it at the moment as a function. It maps the group into the complex numbers. We don't want it to take the value 0 at every group element, so chi is not 0, and it's multiplicative. So in the sense that if chi of x, and if you've got x and y in the group, then chi of x times y is chi of x times chi of y. Simple example of that is to take the cyclic group of order n, which I can write as with the generator x, so 1x up to x to the n minus 1, with x to the n equal to 1. And you simply map each of the powers of the generator to the power of the root of unity in the complex plane. So you map it to e to the 2 pi I on n times a. And you can quickly check then that chi of a times chi of x to the a times chi of x to the b, well, that simply means you multiply e to the 2 pi I a over n times e to the 2 pi I b over n. Index laws say you can write this like this. And then that, of course, is just chi of a plus b, which is chi of a times chi of b. So chi is a character. Now, given any finite abelian group G, we can define a very special character which plays an important role for us, which is called the principal character, and it simply maps every element of the group into 1 in the complex numbers. Clearly this is a character. You might think it's not a very interesting one, but in fact don't despise it, because it does play a very important role, in fact, in the theory that's coming up, this so-called principal character. And I'll usually write it as chi1. So chi1 is our principal character that maps every element of the group to 1. Now, just to get some little results on these characters, some very basic results then. So our first theorem of this section is we've got a character from the group G into the complex numbers. Then if I write 1 for the group identity, that is back in the group here, so I'm going to write 1 for the identity, then chi of 1 is 1. So any character maps 1 to 1. And next very important result, this chi of x then turns out to be a root of unity in the complex plane. And moreover, if I raise for any x, if I take chi of x and raise it to the power, which is the number of elements in the group, then I get 1. Which is simply telling me again that this chi of x then is a root of unity, an nth root of unity, where n is the size of the group. Also, chi of x inverse is chi of x all inverse, and it's just the complex conjugate of chi of x. And for a little proof of that, we have here. So here's our chi maps the group into the complex numbers. We firstly prove that chi of 1 is 1. And these, you've probably seen proofs like this before. They're very simple. You just choose an x in G so that chi of x is not 0. There must be at least one of these, because we said chi can't be the 0 character. And so chi of x then is, I can write as chi of 1 times x, use the multiplicative nature of chi and split this into chi of 1, chi of x. This is not 0, so that has to be equal to 1. So that gets that out very easily. Secondly, of course, that chi is a complex root of unity. It's a complex nth root of unity where n is the size of the group. So again, we take x in G, and we're going to put the size of the group to be n. And so that means every element must have, when I raise it to the power n, I get 1. It won't necessarily be the order of it, but every element to the power of n is 1 from basic group theory. Hence, I can take 1, which we now know is chi of 1. I can replace the 1 with x to the n, and then I can use the multiplicative nature of this to pull the n out the front, and that's it. So chi of x is a root of unity, and we can also find that chi of x inverse then is chi of x all inverse equals chi bar. We want to prove that next, and again we just start off with, we know that chi of 1 is 1. I can write 1 as x be x inverse, split this up into chi of x inverse, and then we can see then that the inverse of chi of x is just this one. This is what you multiply it by to get the identity. Moreover, if omega is a root of unity, then omega inverse is omega bar, since omega bar is the modulus of omega squared. And in this case, these are roots of unity, so the modulus of these is 1. And that then confirms the second part of this, that the inverse of chi of x inverse is equal to chi bar of x. So that's a little basic fact about these things. The second very useful fact is if we take the non-principal characters, if chi is a non-principal character, but the principal character was the one that maps everything to 1, if we take a non-principal character and we sum chi of x over all the elements of the group, then we get 0. And again, the proof of this is not very hard, but gives us some basic sort of ideas and tools that we'll be using elsewhere here. So there it is. If chi is not the principal character, then the sum of the chi of x as x varies through the group is 0. So since chi is not the principal character, then there is an element y in the group, so that chi of y is not 1. There must be an element y in the group such that chi of y is not 1, because chi is not the principal one. So we can then take this sum that we're looking for, this sum of the characters of evaluated x for x in G, and I can multiply it by this chi y. So I can pull this inside the sum and then combine the two together. So this is now the sum of x in the group of chi of xy. Now as x runs through the group, then xy runs through the group. In other words, this sum here is really the sum that we started with back up here, and that means that chi of y times this sum is equal to the sum we started with. Now again, chi of y is not 1, and so I can factor then and observe therefore that this sum here must be 0. And that's a very nice result. The sum of the characters is going to be 0. If you've got a sum of chi of x as x varies through the group is 0, provided you've got a non-principal character. Of course, if you've got a principal character, then when you sum through the group, you'll just get 1 here for every value, and so the answer would be the size of the group. We'll see a slight generalization of this soon. So we can make a couple of observations here then. Observe that for fixed G, once we fix the group G, the set of all characters on G is itself a finite abelian group under the operation of we can combine the two characters together, chi1 times chi2 of x. We're going to define that simply as chi1 of x times chi2 of x for x in the group. So that gives us a multiplication of characters, and under that multiplication then the set of all characters is itself a finite abelian group. The principal character is the identity of this group, which is easy to see because if you multiply each of the characters, if you multiply another character times chi1, well, chi1 just maps everything to 1, so this is going to act like an identity in the group, and for each chi the inverse is just going to be the complex conjugate. Note also that if G is cyclic of order n, then there are exactly n characters for G, since once I've specified the value of chi for the generator alpha of G, because G is cyclic, then for some k we have chi of x. If x is in the group, it's got to be a power of the generator, and that's just chi of alpha to the k. So once I tell you what chi does to the generator, we know what it does to every element of the group. More generally, given a finite abelian group of order n, there are precisely n characters for G. Well, I leave you to give a proof of that as a little tutorial problem to convince yourself that there are precisely n characters on any finite abelian group of order n. And I'm going to write G hat, as a little hat there, hard to see, is it? I'm going to write G hat for the group of characters on G. Now just recall, so we're going to be using it shortly, just recall that this particular very interesting finite abelian group, U sub n, denoted, we saw in an earlier chapter, the set of units in Zn. That is all the elements that are all the x's that are relatively prime to n in Zn, and these also, of course, all the elements that are invertible in Zn. Now these form a group under multiplication, and the order of the group, of course, you'll recall is phi of n, where phi is Euler's totient function. We covered this back in an earlier chapter. You should also recall that Un is cyclic precisely when n is 1, 2, 4, that's a bit of noise, or a power of an odd prime, or twice the power of an odd prime. Now, a character can be completely specified by drawing up what's known as a character table. And that's what I'm going to do now, is to just show you some explicit examples of characters from their character tables. So, very simple one to start off with. We're going to be concentrating, as you'll see, what's coming up on these U groups, and so I'm going to work with these as our examples. So if I take G to be U4, so these are the invertible elements in Z4, they're 1 and 3, and of course 3 squared is 1 modulo 4, and the set of all characters, well, there are going to be 2 of these, there are 2 elements in the group, so there'll be 2 characters, chi1, chi2. So I'm going to specify exactly what the characters do to each of the elements. So firstly there's the principal character, which maps everything to 1, so we just get 2 1s there. And then chi of 1 is always 1, so that fills that element there in. And then chi2, well, can be a square root of 1. Well, there's only 2 square roots of 1, and that's 1 and minus 1, so I'll map this to minus 1. And that gets me the 2 characters for this group. Slightly more interesting example is to look at U5, and U5 are all the numbers relatively prime to 5, which of course are all the numbers 1, 2, 3 and 4. I've put them in this order because 3 is a nice generator. So 3 squared is 4, and then 3 by 4 is 2 mod 5. So I just put them in, I took 3 as a generator and put them in this order. I could have actually put 2 as a generator as well, doesn't matter, but I've just chosen this particular order. Now this group is a cyclic group that's generated by in this case 3. So if chi is not principal, then chi of 3 is any of the fourth roots of unity. So once the chi of 3 is decided, then the remainder of the row is determined. So here's the character table. Firstly, we have, there's our elements, 1, 3, 4, 2. Chi, the principal character, maps everything to 1, and chi of 1 is always 1, so that gets me that there. And now the fourth roots of unity are 1, minus 1, I, and minus I. So for the second character, I'm going to map 3 to minus 1. Now if I square this, if I square 3, I get 4 in U5. So I square the character, I get 1, and then I multiply this by itself again, so I cube this, I'm going to get 2, so I have this times this is going to give me this one, so that fills that row out. Similarly, I could have mapped 3 to I, call that my third character, square that, you get minus 1, multiply these two together, you get minus I, and for chi 4, then I can map 3 to minus I, square it. If I square this one, I get minus 1, and if I multiply these together, I get I. So there is the character table for the group U5, and it tells me exactly what chi does to each of the elements in this set. I want to do a few examples of these so we get a bit of a feel for these. If I take the group U8, now U8 is not cyclic, it consists of 1, 3, 5, and 7. And it's isomorphic to the direct product of two cyclic groups of order 2. So each non-identity element then is of order 2, and 3 times 5 is 7 modulo 8. So the character table then looks like this. So we're going to be mapping things to the 2 square roots of 1, which are 1 and minus 1. There's the principal character again, chi of 1 is 1. So chi 2, I'm going to map 3 to minus 1. And if I square that, I get 1 and multiply these together, because 3 times 5 is 7, I get minus 1. Alternatively, I can map 3 to minus 1, and then 5 to minus 1, and when you multiply these together, you get 1. Or I could have sent 3 to 1, 5 to minus 1, and multiply these, you get minus 1. So there's the character table of the group U8. Now I leave you to do U9 and U16. You might like to have a go at those yourself. Make up the character tables for U9 and U16. And just a slightly different one again is to look at U7. And again, now here I don't want 2 as a generator because it's not. So I'm going to take 3 as a generator of this group. So 3 squared is 2, 2 3s are 6, 6 2s are 4, and 6 3s are 4, and then 4 3s are 5, and then 5 3s are 1 again. So I'm going to take 3 as my generator, and so chi of 3 then can be any 6th root now of unity. So I'm going to put omega then to be e to the I pi on 3. And then I can map, so the 6th roots of unity are going to be 1, minus 1, omega, minus omega, omega squared, and minus omega squared. And again, there's the principal character across there. Chi maps 1 to 1. And once I decide what it does to 3, any of these things, then by just taking powers, that squared is that times that is that times that is that, and so on. It fills out this row. I map 3 to omega, square it, you get omega squared, cube it, you get omega cubed, which is minus 1, and then you again multiply omega to the 4th is minus omega, and so on. And so similarly, as soon as I decide what I'm going to map 3 to, any of these 6th roots of unity, it fills out the rest of the table for me. And so there is an example of the some character tables. We'll have a look at a further example and some of the properties of this in the next video.